this video, we will explore three polar graphs we learned from trigonometry and explore their application through the use of microphones. We learn how to graph polar equations after learning how to convert from Cartesian coordinates, x, y, to polar coordinates, r, theta. These conversions come from the relationships r equal the square root of x squared plus y squared and theta equal tangent inverse of y over x. The first polar graph we'll look at has equation r equal a for a constant a greater than 0. Using the relationship r equals square root of x squared plus y squared, we can interpret the polar equation r equal a as the square root of x squared plus y squared equal a, or x squared plus y squared equals a squared, which we recognize as a circle centered at the origin with radius a. This polar graph is a two-dimensional visualization of what is picked up by the omnidirectional microphone. The prefix omni means all, so this microphone picks up sounds from all directions. In the graph, the microphone would be at the origin, and it would pick up sounds from all of the area in the circle around the origin. This is somewhat similar to how humans hear, in that we can detect sound from all directions. Omnidirectional microphones are perfectly suited to record a sound with its surrounding environment, like an orchestra in a large hall. The next polar graph we'll consider has equation r squared equal a squared cosine 2 theta. If we were to plot this graph by substituting values for theta, we would find problems with certain angles giving us negative values for r squared. In fact, the domain for this polar equation is negative pi over 4 to pi over 4 and 3 pi over 4 to 5 pi over 4, and the graph we get is called the figure of 8. There are other polar equations that give similar graphs, but all of them are related to each other by rotations of this simple graph. A microphone that is figure of 8 is also referred to as a pressure gradient microphone, since it responds to the difference in air pressure from the two sides. When looking at the graph, you can imagine the microphone at the origin, and it has two halves, one facing right and the other facing left. And again, this graph is a two-dimensional representation of the area the microphone can pick up sound. It can pick up sound from both sides, but it won't pick up sound coming from the directions perpendicular to these sides. These microphones are great for picking up sound from one direction, but rejecting sound from another. Here's an audio example to hear the difference. In this example, you can still hear the glass after I turn the microphone, but it is at a much lower volume. The reason for this is the sound is bouncing off of the room and is still able to reach the circle sides of the microphone. Another unique quality of the figure of 8 microphone is that one side will always pick up the inverted or negated electrical signal from the other side. This is easy to understand by considering one particular kind of figure of 8 microphone, the ribbon microphone. The one we considered before is a ribbon microphone, and as sound travels from one side to the ribbon, the changes in air pressure move the ribbon back and forth. Relative to the direction the sound waves are traveling, one direction is positive and the other is negative. When microphones and recording techniques were first developed, the omnidirectional and figure of 8 microphones were the only types used. However, it was discovered that when adding the two polar graphs, a third type of microphone could be made, the cardioid. When we overlay the two images we've seen so far, the positive area inside the red circle adds to the area of the figure of 8, and the result that we get is the graph of the cardioid, seen here in purple. In this picture, the microphone would be pointing to the right and would receive the strongest signal from directly in front of the microphone, less signal to the sides, and then no signal from directly behind the microphone. This is a very common microphone for singers, since only their voice is what you would want the microphone to pick up. In fact, I am using a cardioid microphone to record my voice for this video. We can get the same shape from the polar equation r equal a plus a cosine theta for a constant a greater than 0. The recording of sound has become an important part of our modern world, from the entertainment we enjoy to the ways we communicate. And while there have been variations of microphones over the years, all of these variations are based on the three patterns we've seen and the polar graphs related to them.